Hello everyone, welcome to this video on the flat operator, or an introduction to the flat operator. So the flat operator, also called the musical isomorphism, is a mapping between vector fields and differential one forms on a differentiable manifold M. It is one of the key tools in differential geometry that relates elements of the tangent bundle, Tm, vectors that is, to the cotangent bundle, T asterisk M, covectors or differential one forms. Now the operator depends on a choice of a Riemannian metric G on the manifold. It has an inverse called the sharp operator, which maps differential one forms back to vector fields. All right, so let's make a start. All right, so we'll start with individual vectors instead of the tangent bundle, and then we'll generalize the definition. So the musical isomorphism is a tool that converts between vectors and covectors or their fields on a manifold equipped with a Riemannian or pseudo-Riemannian metric. Pseudo-Riemannian as in general relativity. It is called musical because the notation involves the symbols flat and sharp. All right. So for instance, we have a manifold M. We have a point on that manifold MP. We have the specific tangent space to the manifold at the point P, so tangent space to the manifold at point P, and we have a vector X there, and any other vectors that live in that tangent space or exist in that tangent space. Then the flat operator is a map from the tangent space to the manifold M at the point P to the cotangent or dual tangent space to the manifold M at the point P, so the cotangent or dual tangent or dual space. Okay, and here's our vector X in the tangent space, and here it becomes a one form in the cotangent space, both at the point P. Both the tangent space and the cotangent spaces are coincidents together at the point P, but obviously I can't draw them on top of each other, otherwise it'd be a very messy, confused diagram. So I separate them, but they both occur at the same point P. Okay, tangent bundle is then the collection of all these tangent spaces, and the cotangent bundle is then the collection of all the cotangent spaces. All right, so our flat operator, what does it look like? What does it do? All right, maybe I should get rid of that. So definition of the flat operator. So for a vector field X, written in terms of its components and basis vectors, xi, partial xi, its corresponding one form, x flat, has the form x flat is the flat of the vector field x is xi dxi. Notice the components here, x upper index becomes x lower index, all right? And these basis vectors become basis one forms. All right, it is defined by x flat is g of x and insert a vector in there of any choice, where G is a metric tensor, and the second argument represents a dot indicates that G acts on any vector field. Its operation there is it takes a vector and contracts it with another. So X flat is a differential one form. All right. It acts on a vector Y, let's say, to produce a scalar. So X flat operating on the vector Y is just the inner product under the metric G of the two vectors x and y, where g, x, and y is the inner product of x and y under the metric G. Now, in tensors, we recognize this as the lowering of the indices here, the lowering of the indices, okay, and later on we'll come to that, and we'll see how that works under a general metric. We'll start off with the Euclidean case, where you'll see that in the Euclidean case, x upper index I is the same as x lower index I, because the metric has for each element in the metric G, each component is one. All right. So the flat operator, flat, maps a vector x to a one form xb. So I'll show you a bit more of that. All right, so applying the flat operator in R3. So we're in Euclidean space. So in R3 with the standard Euclidean space, the metric G is just the diagonal matrix 1, 1, 1 in the diagonals and 0 everywhere else. So in the calculations, we're just multiplying, G11 will just be 1. So it doesn't change anything. So the musical isomorphism becomes simpler because G can be represented as the dot product, specifically G, or the two vectors x and y contracted under the metric G, is just the usual scalar product of the two vectors x dot y. Now, representing x and x flat, so let's suppose x is given by this vector here, x1, partial x1, and so on and so on. And the corresponding one form, x flat is x1 lowered, dx1. So we've gone from the basis vectors to the basis 1 forms. And the components here, x1, upper 1, contravariant index 1, and x covariant index 1, we're going to see that these two components are the same. So the components xi remain the same. So x upper I is equal to x lower I, but their interpretation changes. All right, so in the vector field x, these are coefficients of the basis vectors, partial x1, so the x upper I, x1, x2, x3, upper index. And in the one form, x flat, these are coefficients of the basis 1 forms, x lower I, x lower 1, x lower 2, lower 3, okay? So dx1, dx2, dx3 are the basis 1 forms. So for example, let x equals this object here in R3, the corresponding x flat is x dx, y dy plus z dz. Notice here the basis vectors become the basis 1 forms, but in Euclidean space where the metric is just that diagonal 1, 1, 1 in R3, then these components don't change. Right? They remain the same. And if y is this vector here, then x flat acting on y is the same as the inner product of x and y under the Euclidean metric. So it becomes ax plus by plus cz. All right. So again, just remind ourselves, we have the tangent space of the manifold at point P. We have a vector x in there, or any other vectors in this particular tangent space of the point P to the manifold M. We have the cotangent space at the point P, which contains the one form x flat, okay? And the flat operator is a map from this tangent space to this cotangent space. So the correspondence x to x flat via the flat operator is fundamental in differential geometry. It allows us to switch between vector fields of one form seamlessly, leveraging the metric structure. We're going to see a little bit more about that metric structure when we generalize our definition a bit. All right, so let's go to the general definition of the flat operator. So given a Riemannian manifold M and a metric G on it, the flat operator is a map flat from the tangent bundle to the manifold M to the cotangent bundle to the manifold M. So that takes a vector field X belonging to the tangent bundle to the manifold M and associates a differential 1 form, X flat, that belongs to the cotangent bundle to the manifold M, defined by X flat operating on a vector Y is equal to Gxy for all vector fields Y belong to the tangent bundle of the manifold. And notice here, instead of the Euclidean metric, this can take on other forms, and we'll see examples of that. So here, G of xy is the Riemannian inner product of the vectors x and y defined by the metric G. To be a little bit more specific, let's have a look at it in local coordinates. So if x1, x2, xn are local coordinates on M, some patch of n, some coordinate chart on M, and the metric tensor is written as G as Gij dxi, tensor product with dxj, then for a vector field x equals xi partial xi, so you can expand that out for depending on I going up to n, then x flat will just be the flat of all that, which will be Gij xi dxj, where now these metric coefficients are not, or components, are not all one, and will depend on the space you're in. Each space will have its own metric. And they will lower this index, and so will produce a different result. So the components Gij represent the local expression of the Riemannian metric. I'm going to give you an example shortly, but first I'll just go back to Euclidean space with a simple metric, and we'll do that in 2 dimensions, and then we're going to look at a different example from general relativity. So here, I'm just reminding you again with a simple Euclidean metric, Gij is this diagonal matrix, 1, 1 in the diagonals, 0 elsewhere. Okay, so let x be just the vector partial x, so just the basis vector in the x direction. Then x flat is the flat of all that, is just simply the basis one form dx. All right, let's say we've got y as this object here, then the flat of that will just be x dx plus y dy. Notice the x here and the x here haven't changed, the y here and the y here haven't changed, because we're in that Euclidean metric. These components of the metric are 1, and they're not changing anything. X times 1 is just x. Y times 1 is just y. But in other curved spaces where the metric is not this simple diagonal identity matrix, this is going to change. And that's our next example. All right, so the Schwarzschild metric contains describes the space-time around a static spherically symmetric massive object, and is given in Schwarzschild coordinates ct r theta phi by. So here's our metric, our space-time interval, our line element. Okay, and the Schwarzschild metric can be written as g mu nu is this object here. Everything in the diagonals here, but they're not ones. And so what's the effect of that? Let's have a look at that. Okay, so let x be a vector field expressed in Schwarzschild coordinates. So x is this, each of the coordinates, in basis vector in each of the coordinate directions, basis vector in the ct direction, basis vector in the r direction, theta, phi directions. Then to compute x flat, we apply the flat operator using the metric components. So x flat now becomes, see these metric components, times the vector component, over this vector component here. And the effect of that will be to lower this component to produce, okay, here xt is the contravariant component, and when we lower it with the metric component, the corresponding metric component, we'll produce a covariant component. All right, so all of these along here. So to demonstrate that, let's just take a simple case. So let's assume x is a purely radial vector field. X now is just in the radial direction only. So we have some vector pointing in the radial direction, scaled by this component xr. Applying the flat operator, x flat, is grr xr dr, or just the flat of that whole thing, which I haven't written here, but I've written now in terms of its components. So it's grr, covariant rank 2 component, grr, xr dr, and that component grr is given by this, times the vector component xr dr. Now, if xr is, just for sake, let's just say xr is equal to 1, just again simplifying to make this, just to demonstrate a point, okay? We could have had 1 up here, okay? A unit radial vector, the 1 form becomes x flat is just this, the grr component, times the basis 1 form dr, okay? So this result shows, now we didn't get that in Euclidean space, because remember these GRRs and all the rest in Euclidean space would just be 1s. But in a curved space, they're not. Generally not. They're not going to be. And so we have these components here, and they affect our vector. If our vector here had other terms in it, well, we'd be multiplying by that as well. So this result shows how the flat operator transforms a radial vector into a 1 form. So we've gone from a vector here to a 1 form, from vector x to x flat, the 1 form. Scaling it by the inverse of the Schwarzschild metric component grr. All right, now interpretation. Now this scaling factor here reflects the curvature of space-time due to the gravitational field, and the flat operator accounts for the geometric distortion introduced by the Schwarzschild geometry, effectively encoding how distances and angles are perceived differently in curved space-time compared to flat Minkowski space. Okay, properties of the flat operator. It's linear. The flat operator is a linear map over the space of vector fields. Isometry. The flat operator preserves inner products, angles between vectors. So the inner product of the vectors x and y is the x flat operator acting on y for all vector fields x, y. The inverse sharp operator now. Now this is the inverse operation. So the flat operator has an inverse called the sharp operator, sharp, which maps differential 1 forms back to vector fields. Remember, the flat took us from a vector field to a differential one form, and now the inverse map, the sharp operator, goes from the differential one form back to the vector field. So sharp is a map from the cotangent bundle to the manifold M to the tangent bundle to the manifold M. Okay, so for a one form omega is omega I dxi, then the flat operator is omega flat is the flat of all that. Sorry, not flat, the omega sharp, sorry about that, omega sharp is the sharp of that. Okay, raising it. So we get now G contravariant indices ij, upper indices ij, times omega I, and the basis one form becomes the basis vector, partial xj, where Gij are the components of the inverse metric tensor. All right, so the inverse. Now, given the previous, you've seen the Schwarzschild metric, well, the inverse of that is just the reciprocal of each of the diagonal elements. Okay, so application of differential geometry, so gradient. The gradient of a scalar function f on a Riemannian manifold is defined as df is the flat of del or nabla f. Or another way of putting it, because flat and sharp are inverse to each other, nabla or del f is the sharp of df. Musical isomorphisms, the flat and sharp operators establish an isomorphism between vector fields and differential one forms, allowing seamless transitions between geometric and algebraic representations. All right, Hodge theory. The flat operator plays a role in defining the Hodge star operator, and I'm going to be looking at some of that in future videos, which is crucial in the study of differential forms and cohomology. Conclusion, right, so the flat operator, flat is a fundamental tool for translating between vector fields and differential one forms on a manifold. By leveraging the Riemannian metric, it captures the geometric structure of the manifold and facilitates many essential constructions in differential geometry. Now, complementing the flat operator is the sharp operator, sharp, which performs the inverse transformation, mapping differential one forms back to vector fields. Just as flat uses the metric to contract vector components with the basis one forms, sharp applies the inverse metric to raise indices, which we saw on the previous slide, restoring the original vector structure. So the interplay between these operators highlights the duality between the tangent and cotangent spaces, enabling smooth transitions between coordinate-dependent and coordinate-free representations of geometric objects on a manifold. All right, next now we come back here, and then finally a picture to represent all this. So here's our manifold M, here's our point P on that manifold M, and the tangent space to the manifold at the point P, and a vector in it. Then we've asked ourselves what is the flat of that vector, and the flat is a map from this tangent space to this cotangent space, so it maps this vector from here to a one form here. The vector exists in the tangent space to the point P on the manifold here, and the flat of that is a differential one form which exists in the cotangent space to the manifold M at the point P, hence the asterisk, upper asterisk, and it is a one form here, X flat. And then the inverse map takes the differential one form and raises it again to the vector. So it maps it from the cotangent space to the manifold M at the point P and maps it to the tangent space to the manifold M at the point P. And likewise, since P is arbitrary, we could be talking about the tangent bundle to the manifold and the cotangent bundle to the manifold. And this sharp operator raising forms, differential one forms in the tangent bundle to the manifold, cotangent bundle to the manifold, raising them up to the tangent bundle to the manifold. But in this particular case, I've chosen a specific single vector space, tangent space, and I've shown you the maps between the two. So the sharp operator goes from the vector space to the differential form space, from the tangent space to the cotangent space, and then the sharp operator goes from the cotangent space to the tangent space. Well, what I should be saying, taking objects in these and moving them from one tangent space to another. All right, that's it. I hope you found that useful and informative, and I shall see you in the next video. Take care, everyone. Please, if you will, subscribe, push the like button at the very least, I hope, and subscribe to the channel if you will. I greatly appreciate that. Thank you, everyone. Have a good day, and I'll see you in the next video.